Okay, final video here. I'm just going to go through 3 more examples. Just practice, okay? Each morning, when Harold has a shower, there is a 90% chance that the hot water is working. The probability that Harold has a long shower is 80% if the hot water is working, and 10% if the hot water is not working. Okay, find the probability that on any given day, Harold will have a long shower. Okay, well, what we need to do for this is do a tree diagram, okay? So there are a few events happening here. One is the hot water could be working, or the hot water might not be working. And there's a 90% chance that it's working. Now, don't ever do tree diagrams in percentages. Change it to a decimal, because you'll get it wrong when you try to multiply the percentages. For example, 90% times 20% is not 90 times 20. It's 0.9 times 0.2, and then change that into a percentage. Okay, so change things into decimals. And clearly, if there's a 90% chance of the hot water working, there's a 10% chance that it won't work. Okay? The probability that Harold has a long shower is 80% if the hot water is working. So if the hot water is working, he'll have a long shower. If it's not working, he won't have a long shower. And there's an but he could also not have a long shower. There's an 80% chance if it is working, so that's 0.8. So this must be 0.2. Okay? If the hot water is not working, there's only a 10% chance. So we'll have a long shower, it's only 0.1. And the chances of not having a long shower are very high, 0.9. Okay? So now, no lazy tree diagrams. Outcomes are hot and long shower, hot and not a long shower, not hot and a long shower, not hot and not a long shower. Associated probabilities are 0.9 times 0.8 is 0.72. And then so it's going to be 0.18, 0.01, 0.09. Again, you can check that they all add up to 1 to know you've got it right. So find the probability that on any given day, Harold will have a long shower. So what is the probability, this is part A, the probability of a long shower is anything where he actually has a long shower. So he has a long shower here, and he has a long shower here. So it's this or it's this. So the answer is 0.73. Changing it back to percentages now, it's 73% chance of having a long shower. Okay? During a 365-day year, how many long showers would you expect Harold to have? Well, that's just an expectation question. So you've got 365 opportunities where 73% chance of having a long shower. Multiply them together. Appears to be 266.45. So it's approximately 266 long showers per year. Okay? I hope that makes sense. So don't use percentages. Okay? Do not use percentages because you'll get things wrong. You can put them back to percentages at the very end of the question. Okay, Matthew is taking a mathematics test. There is a 2% chance that his calculator will not work. If his calculator works, Matthew has 70% probability of passing the test. If his calculator does not work, Matthew has 55% probability of passing the test. Find the probability Matthew passes the test. So, his calculator can work, or his calculator cannot work. Seems to be that the probability of his calculator working is 0.98, but 0.02 of it not working, 2% chance. If his calculator does work, he could pass, or he could not pass his exam. 0.7, therefore 0.3 of not passing. But if his calculator does not work, he only has a 55% chance of passing. So he has a 45% chance of failing. Okay, no lazy tree diagrams. So his calculator can work and he can pass. Calculator work and he can fail. His calculator cannot work and he can pass. His calculator cannot work and he can fail. Associated probabilities, we're using a calculator. 0.98 times 0.7 equals 0.686. And then if I change that to 3, so 0.98 times 0.3 equals 0.294. Okay, and 0.02 times 0.55 equals 0.011. And 0.02 times 0.45 equals 0.009. Again, you can check they all add up to 1, which they do. So find the probability that Matthew passes the test. That's this, or it's this. So the probability of passing is equal to 0.686 plus 0.011 equals 0.697, which is 69.7% chance of passing this test. Okay? Last question. A ball is selected from box A and placed in box B. A ball is then selected from box B and placed in box C. A ball is then selected from box C. Find the probability that the ball is blue. This is a bit of a nightmare, okay? But you just ration it out, logic it out. It's quite straightforward. So the first event is box A, and we can take a blue or a red, and it's going to be 2/3 and 1/3. Now we've got to consider that what we're doing is we are putting whatever we took out of box A into box B. So that means if I took a blue out first, I've now put a blue into box B. So what are my probabilities? I can still take a blue or a red, but the probabilities are 4/5 of blue and 1/5 of red. Sorry. But if I took a red out of box A, I could still take a blue or a red from box B, but the probabilities have changed now because I didn't put a blue in, I put a red in. So that changes the probabilities. This is definitely dependent variety. So it will be 3/5 for blue and 2/5 for red. Now we go to box C. Again, I can take blue, red, blue, red, blue, red, blue, red. What's happened here is I've now put a blue one into box C, where it's going to become 3 out of 6, and red is 3 out of 6. So that is the same for any time I put a blue in there. So look at these need to be the same. But I may have not done that and may have put the red in which case it's only going to be 2 out of 6 for blue and 4 out of 6 for red, and that's the same for any time that I did a red. So 2 out of 6, 4 out of 6. Don't be lazy, okay? Do your proper outcomes. So I can basically select a blue, 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 red, blue, red, blue, blue, red, 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 blue, blue, red, blue, red, 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 blue, and red, red, red. Probabilities are, where I got the denominator is always going to be the same, 3 times 5 times 6 equals 90. So the denominator is always 90. And 2 times 4 is 8, 24. Oops. What's that? This one's going to be 2 times 4 times 3 again, also 24. Stop doing that, please. 2 times 1 times 2, that's going to be 4 out of 90. 2 times 1 times 4 is going to be 8 out of 90. Ugh, stupid iPad. 9 out of 90. Then again 9 out of 90. Then 4 out of 90. And 8 out of 90. You can check that all out to 1. So a good non-lazy tree diagram. I can now try to answer the question. So it says a ball is then selected in box C. Find the probability that the ball is blue. So actually all it wants to know is what is the probability that the last ball we pick is blue. Well, that would be 1, that would be 1, that would be 1, and that would be 1. So what I've got to do is add all of them up together. So it's going to be 24 plus 4 plus 9 plus 4 all over 90. Which is equal to 24 plus 8 is 32 plus 9, 41 out of 90. Probability of taking a blue from box C. Okay? I hope all of that makes sense. The best way to be good at doing tree diagrams is practice, practice, and more practice. Okay? So